Hello everyone. Today we are going to jump a little into environmental analysis with Ladybug inside Grasshopper. So what we are going to be learning today will cover installation of Ladybug inside Grasshopper, how to do some solar analysis, how to do some wind analysis, and then some view shade analysis. Let's get into it. So let's start with the installation. If you go into the site Food for Rhino and search for Ladybug, you will have Ladybug tools. Remember that to download, you have to log in into the website, and at the time of this recording, you can log in to this website with your Rhino account. It's a free account that you can create in the Rhino website, so do that. So after searching for Ladybug tools, click on it and then click on download. This will take you into this table, and you'll see the topmost one seems to be the latest that we have. So let's download that, and it works for Rhino 6, 7, and 8. So whatever version you're using, you can use Ladybug with it. So hit download and save it. So I'll create a new folder named plugins, and inside that Grasshopper. Then I'll save it over there. So zip file will download. Let's open the folder location of that zip file, which is over here, and extract all. So after extraction, you'll see this folder. So get into that, and you'll see there's an installer named installer, like an installer Grasshopper file named installer. So you have to run Rhino at this point and run Grasshopper and then run this installer file. So let's do that. And here's our Rhino. I'm running Rhino 7, but this should work with Rhino 8 as well. So here you can see this small button called Launch Grasshopper. So click on that. Grasshopper will launch. And then we'll have to open that file, that installer file, into Grasshopper. The easiest way to do that is just drag and drop it inside Grasshopper. And here it comes with instructions. It says you have to be connected with the internet, and this is the first step. So if you're unfamiliar with Grasshopper, these are some visual scripting tools. The left side is an input, the right side is an output, and I'm planning to create some Grasshopper tutorial series really soon. But for this specific tutorial, all you need to know that this toggle is a Boolean toggle, and if you double click on it, this will become true, and this will execute this script, and your whatever script that you may have will run inside Grasshopper. So let's double click on it and wait a little. It's installing. I can't move anything, as you can see, because Grasshopper is working in the background. But after it's done, you'll see Ladybug tool installation folder created at this directory. So let's install Ladybug now. It's a very nice button. You see, it's fun. You can see that I don't have any Ladybug tool sets here, but after I install this, we'll have it. So it's still installing, but after it's done installing, we'll have to restart Rhino and then run Grasshopper again, and then we'll be able to see the Ladybug and Honeybee tools. For this tutorial, we are not going to talk about Honeybee. We're only going to talk about Ladybug and some environmental analysis with Ladybug. It's taking a while. So I'll jump ahead. Now you can see Ladybug Tools 1.8 has been successfully installed. Restart Rhino to load the components. So I'll do that. So before we run Rhino again, I'm jumping ahead a little bit to make our life a little bit easy. uh, we'll need sky matrix quite a lot for solar analysis, and to do solar analysis right, we need to have some Radiance apps installed. So I'm going to install those first, and then restart Rhino, because otherwise I cannot create Sky Matrix as I need. So this is the version of Sky Matrix that worked for me. Not Sky Matrix, sorry. This is the version of Radiance that worked for me. And we'll also need OpenStudio. So we'll install OpenStudio as well. So I'll paste all of these GitHub links in the description section. But let's install this. So to install this version, all you need to do is click on the link for Radiance and then click on Assets. If you're using Windows, you can download the exe. If you're using Mac, I'm not sure, but maybe PKG. I'm not entirely sure. But I will install the exe of this Radiance version. So just click on that. This will download in the same folder. While that downloads, I will also get my OpenStudio. Similarly, you'll have to click on the assets and then download the exe. And then all you need to do is you need to just run the exe file one by one with no particular order, and then you'll have to restart your Rhino. So yeah, I'll do that and then come back to you. Now that we have installed Ladybug, we'll see that if we run Grasshopper, we have all these new tools. So Ladybug is right over here, but we also have Honeybee, Honeybee Energy, and Honeybee Radiance. I guess these are installed because we also installed OpenStudio. I'm not sure. Please correct me in the comments. But here's the Ladybug. And the main component of Ladybug is lb import EPW. And you'll see that it takes an EPW file as an input, and I'll show you how to do that and where to get your EPW files from. But it gives you a lot of different outputs, which we could connect with a lot of different components of Ladybug, and we are going to use some simple components to create some simple weather analysis and weather diagrams. So yeah, let's start. Let's talk about where we can find the EPW files first. So let's search for EPW Ladybug, and you'll see the first result that comes into Google in a Google search is EPW map inside Ladybug tools. So essentially what it is this is a world map where different weather files or EPW files could be found. So what are EPW files? EPW files are authoritative energy plus files, which has some very important data that we need to create locational environmental analysis. So this is extremely important because like wherever we are around the world, we need to create our designs local to the site. So let's search for Lubbock because that's where I'm located. It gives me Lubbock, Texas, United States. And this is just the location, but you'll see that mostly weather files are generated near the airport of the city. So let's download this. The different colors are different sources. So let's work with this one. So just click on that point and hit download. and let's save it. A zip file will be downloaded. As you can see, it's a very small zip file. So let's right click and extract. And this file shows up. So this is the EPW file we need. So how do we get this inside Grasshopper? So I'll just copy the file path. Inside Grasshopper, I will go to params and, or not like that. Let's just double click and type in file path. So this is how you find any command inside Grasshopper. You just double click in the empty space of Grasshopper and search for the component. In my case, it was file path. Right click, select one existing file, paste that, and here you'll see it's loading, and it has become gray. So let's talk a little about color codes inside Grasshopper. Whenever something is gray, it means it has data and it should work. Whenever something is orange, it will usually throw an error, and that error is an input is missing. So in theory, if I just connect this with this, like the output of the EPW file to the EPW file as an input, this will turn gray. And yeah, it has become gray, which is great. We know now that it should work. And then if it becomes red, it's an error that you need to fix. It's not an input issue. So yeah, if something like that occurs, we'll talk about it here. Let's go into Ladybug. And the first thing we need to talk about is Sunpath analysis, as well as some time periods. Let's talk about both of them. Let's talk about time periods before we talk about Sunpath. So here, if you click on Analyze Data, you'll see LB analysis period. So if you click and drag it here, you'll see a start month, start day, start hour, and end month, end day, end hour. So what essentially we can do with this is we could create different seasons, and then we could like use those seasons for seasonal environmental analysis. So I'll do exactly that. I'll do a small Google search, and then I'll create winter, summer, fall, winter, spring. So yeah, those seasons. So let's do that. So I did a little Google search, and now I know that winter is from December to February. So I'll do that. So all of these are number sliders, and I'll do exactly that. So to create a number slider, you need to double click and type in a random number. Let's type in 12. Um, so it can go from 0 to 100 by default. But for month, we know that the maximum number of months that we can have is 12. So double click on the number slider, make the max 12, and let's change the name into month. Awesome. Now you can see that it's like from 0 to 12. For like another layer of caution, we could just add the lowest to 1, because 1 is January, 12 is December. So now the lowest is 1 and 12 is highest. And you can just drag this slider from 1 to 12 to your liking. So that will be connected to my start month, because we know winter starts at January and ends at December. So now we need a start day. So let's create another random number, double click, make the highest 31, because that's the number of days a month can have. Let's make lowest 1, and let's make this name to month. All right. And hour. So another random number. And yeah, this we could create into decimals, but let's keep it simple. Double click, start will be 0 here. That's the first hour. End will be 23. And let's make it hours. It's not 24 because 24 becomes 0 again. So 0 to 23 equals 24. So let's connect all of those. Let's make them aligned. Copy and paste. And then let's connect them again. Oh, sorry. So we know that the start month is going to be 12. Oh, that should have been day. Let's correct that. This should be day 2. So day is going to be 1. Hour is going to be 0. And then our end month is going to be 2, which is February. Our day is going to be 28. And our hours are going to be till the last. So this now represents winter period. So let's do a scribble and double click on this and write it winter so that we don't lose track. Now what we can do is we can copy and paste all of this. That's just Ctrl C and Ctrl V, and for Mac that would be Command C and Command V. Let's create the other seasons as well. So let's create spring. So spring is from March to May. So start month is going to be 3, day 1, hour 0. And it ends at May. So that's going to be 5. This is going to be 31 because May has 31 days, and this is going to be 23. That's spring. Let's create a summer. So summer is from June to July. Is that right? January, February, March, April, May, June, July, August. So June to August. So let's do that. That's going to be 6. And this is going to be 8. That's August. So everything else should be the same. And let's create a fall. So fall is from September to November. So let's do that. 9 to 11. And this for November is going to be 30 because November has 30 days. So we have all our seasons. Let's make a group out of them so that they are in a nice place. Let's give a scribble, which is seasons. So now we have all the seasons done. It's not doing anything for our Rhino, which is okay. We'll get into that really soon. But it's important to understand what we are getting as outputs. So we can see period as outputs, and we can see HOYs as outputs. So HOYs are hours of years, which are some number list. Most of the Ladybug tools now in 2024 uses HOYs. You'll see that if I just drag and drop a Sunpath, which is right over here in visualize data, you'll see you have HOY. So this HOY will be connected with this for the period we want to analyze. But some will also have your periods. So this is very important to create periodical environmental analysis. So that's how you create seasons. So let's start by creating a basic sun path. So before I do that, let's talk about what a sun path is and how to work with it. So a Sunpath diagram is a graphical representation that illustrates sun's trajectory across the sky at a specific location throughout the year. It's very important to understand Sunpath because this gives us uh, like the guidelines for our design decisions. So you can see that for this specific position, the solar position is over here. These represents different months and then lines of constant time for each. And these dotted lines that you can see would be the location of the sun at that time. So remember that we created different seasons to understand where sun will be staying. So that's one thing to understand. The next thing that we need to understand is how sun behaves around the year. So by common sense, we can tell that sun is higher in the summer and it gets lower as we move towards winter. So these angles, they change. So the horizontal angle and the vertical angle, both are very important and they are called azimuth and altitude. So the horizontal angle is called the azimuth and the vertical angle is called the altitude. So let's talk a little about them. So azimuth angles are the angles that indicate the sun's position relative to true north, measured clockwise in degrees. So if you are here, you are the observer, and this is your true north, and this indicates the rise of sun and this setting of the sun. If you connect your standing point with the rising point, and then measure this angle right here, this would be azimuth angle. Similarly, the altitude represent the sun's height above the horizon, measured in degrees. So if you connect the rising of the sun to the point of the sun you want to measure, or like the point of the horizon and the location of the sun, this angle would be the altitude angle. So if you're like me, living in northern hemisphere, during summer the sun rises north of due east and sets north of due west. This results in a longer arc across the sky, leading to extended daylight hours. And for the winter, it's the opposite. It's rises south of due east and sets south of due west, creating shorter arc and shorter daylight period, meaning shorter azimuth. Similarly, in summer, altitude angles are higher, and in winter, altitude angles are lower because sun is higher in the summer and lower in the winter. So now let's talk about Sunpath in Ladybug. We have created all these seasons. So all we need to do now is get into visualize data and create LB Sunpath. It asks for a lot of things, so let's see what it needs. So it asks for a location, which we can get from here. It asks for HOYs, which we can get from here. Let's do a summer first, and then let's compare that to winter. And basically at this point, we should have a sun path. So let's extend my perspective view. You can see that we have a sun path for summer. You can see we have all the datelines. We have azimuth, altitude, all accurate to Ladybug's International Airport. So that's great and all. You can see that we can also change the HOYs and our sun path should change. You can see in winter sun comes more to south and at a lower altitude angle. At spring it becomes something like this. At summer it goes all the way up, and then if you go back to fall again it will look something like this, which is awesome. This is great. We can work with this, but it doesn't give us the temperatures, which we can also get from the dry bulb temperature. So you can see there's a thing called data. So you can add your dry bulb temperature to your data, and then you'll have this beautiful, beautiful visualization of temperature. So this temperature is given in degrees Celsius, and you can see how much temperate it gets um, in relation to different times of the year. So in winter, if you connect winter with the HOYs, you'll see this gets pretty low. Most of the time, it's near like 0 or very near to like, I guess maximum is 27 degrees, but yeah, it's pretty low. And then if you go to summer, it will become very contrasting because Ladakh is pretty hot. Highest is 38 degrees Celsius or 39 degrees Celsius. So yeah, this is nice. We can get all of this very nicely. And this could act as the first step of our design. So that's how you create an interactive Sunpath diagram. So another similar visualization that we could do with Ladybug is a sky dome diagram. So sky dome is essentially a hemispherical representation of the sky as observed from a specific location of the ground. So let's do that. Let's create our first sky dome. So you can see LB sky dome. So at the very beginning, the first thing that it requires is a sky matrix. So let's talk about what a sky matrix is. So sky matrix quantifies the amount of solar radiation arriving from each patch of the sky dome over a specific period, such as an entire year or maybe the seasons that we created. So let's get our sky matrix. So this is the cumulative sky matrix, and this is what we are going to use, but you could also use the benefit sky matrix, but let's just use the cumulative sky matrix. So here it asks for a location, which you can get from your EPW file. Your direct radiation is going to be direct normal radiation from the EPW file. Your diffuse radiation is going to be this. Your HOYs are going to come from your analysis periods. So let's start with the summer first. And now we have a sky matrix. The thing is, it doesn't show anything in the viewport because a sky matrix is like the calculation for the sky dome. It doesn't show anything. It's just the numerical representation that assigns radiation values to each segment of the sky. So if you click on the sky matrix, you'll see like one locally defined value from Labak International Airport, which is okay. Now let's connect this to our sky dome, and we have the sky matrix right over here. We can see it's quite similar to our Sunpath diagram, but it's a bit more easy to read. So if you're working with something three-dimensional, this could come in handy, and then you'd have a very nice understanding of what kind of shading should work in your summer sun. Because we connected summer, if you're worried about winter for some reason, you could always change your HOYs to winter, and then that changes. So this again is a very interactive diagram for your sunlight visualization. One similar thing that we could do is radiation rows diagram. So let's do that while we're at it. So let's delete our sky dome. Let's type in radiation rows. So that's LB radiation rows. It also asks for a sky matrix. So let's connect that, and we have a nice radiation rows diagram. So this is the radiation rows for winter. You see it comes with kilowatt hour per meter square, meaning that it's kind of the energy the ground is getting from different directions. So which is great. This we could directly use for our environmental visualization, and if you're working with, say, a building or a kind of a interactive facade where we need some dense shading where sun is going to be at its hottest, we could get directions from here directly. So these are the three ways we could get. One is the Sunpath diagram, the another is sky dome, and then the other is sky matrix. So let's create them side by side. They don't have to be at the center point. You can see uh, there's always a center point component into our radiation rose component. So we could use different points to create centers for different uh, visualizations. So let's create two more points, one for our sun path. Again, location is going to be this guy. H of y is going to be this. And we should have a sun path, and this asks for a center point right over here. So let's create a point, double click and point, right mouse button, set one point and this, and connect that to the center point. So that's our sun path. Let's connect dry bulb temperature with data. So we have that. And for our sky dome, let's create a sky dome. Connect the sky matrix. We need another point. Connect the center point, and we have a sky dome. So these are the three different types of solar diagram we were going to talk about in this tutorial. So again, that's sun path, sky dome, and radiation rose. All of these are very much interactive, and you could like work it out with different seasons. So yeah, that's great. Now let's talk a little about uh, incident radiation analysis. So what is an incident radiation analysis? This essentially involves evaluating the amount and distribution of solar radiation that reaches a specific surface or area. So let's say we have these as our context, and we want to understand how much heat the ground is getting or how much energy the ground is getting. We will use the incident radiation analysis. Let's start with that. We will have all of this as before. I deleted all the solar diagrams that I created a bit earlier, but we do need the sky matrix, the EPW file, and the seasons. Now let's get our analyzed geometry, and it'll be incident radiation. So here it also asks for a sky matrix, which is this. Here you can see it asks for geometry and context. So the easiest way you could do that is to create boundary representative objects or BREPs and deselect everything in Rhino. Right click on the BREP. Let's create the context first. So set multiple BREPs because we have multiple buildings. So this, and this are going to be our context. Let's create another BREP. Right click, set one BREP, and this is going to be the ground. So we have everything inside Grasshopper. Let's connect that to the geometry, and let's hide everything from Rhino so that we have a better understanding of what's going on in terms of analysis. That's great, but it's still orange. So what's wrong? Let's see. It asks for input parameter grid size failed to collect data and input parameter run failed to collect data. So let's do that. Grid is essentially grid size, and Grasshopper don't have any inherent units. It inherits the unit from Rhino. I created this as feet, so if I say write five, this is going to be 5 feet. Let's connect that to grid size, and then we need a boolean. So boolean toggle for our run. By default it's false, which is okay. It's a good practice to save everything at this point because you never know when your file's gonna crash. So I'll do that. I'll save everything and then run this. So now that I have saved everything, let's run this. So all I need to do to run it is double click on it, double click on the boolean, and it will start calculating. So let's give it some minutes. It's working very hard. And as soon as it's done, you'll see the solar incident radiation analysis. So it's a bit fuzzy because it has two layers overlapping. So I'll just uh, hide the preview, not unhide, and you'll see that wherever the buildings are at, the radiation is very low over the shadow of the buildings, and wherever there's no shadow, it's very high. And this is again kilowatt hour per meter square. This was done for winter, so let's see how it goes with summer. Again, you can change that with the HOYs inside the sky matrix. So let's connect HOYs from summer with the HOYs from the sky matrix. Wait a little because it's calculating a lot, and then we'll see the summer analysis. So here you can see the summer analysis is a bit more hot than the winter. So let's see how this works out with kind of shading if we create something over here. And for the next step, I'll lower the grid size as well. So what is grid size? Grid size is the resolution essentially. So 5 means all this is calculating at a 5 feet by 5 feet grid, and that's why like this is a bit fuzzy. The more I make it smaller, the more finer it's going to get. So yeah, sorry for the bad English. So let's do that. Let's create a shade. I'll speed up the process. So now we have the shade we need. So let's get back into Grasshopper. Let's change the context. Let's make it false first so that it doesn't take up all the memory that we have. Let's set multiple breps for the context. This, and this time I'll include the shade. And now if I hide everything and run, you'll see a slight change. I forgot to change the grid size, but let's keep it at 5. This is pretty good. So you can see it directly affects the heat gain. And wherever there are punches, there are some solar radiation, but mostly there are no incident radiation. So this is great for understanding the impact that we are having in terms of shading device design, planting design, and how much accessible an outdoor space is going to be in terms of radiation. So that's how you do an incident radiation analysis. Now let's talk a little about another similar solar analysis called direct sun hours. So you can find that over here. So analyze geometry and LB direct sun hours. It asks for vectors, and if you hover over it, it tells you that it gets the vectors from LB Sunpath. So we do need the Sunpath one more time. So let's get our Sunpath, and from the EPW, let's connect the location. Let's do it for the summer. So let's connect summer HOYs. And center point could be over there. It's fine. We are going to work with this. And then let's get the data from dry bulb temperature. So we have all of these. That's great. So now you can see that in direct sun hours, it has vectors, so let's connect the vectors. Our bref for the geometry is going to be, sorry, I grouped it twice by mistake for no good reason. So if I enable the view, you can see that it has that ground with this. So let's connect that as a geometry. Let's connect the context, our buildings and the shadings, all of this together. And let's create a grid size of 5 because this may take a while. Let's save the file. And let's connect that to our grid size. It takes a while to save because I'm also screen recording. So yeah. And now we have to run it. To run it, we have to get a Boolean toggle, which is this. Let's connect that. And if we hit run or double click on the false, it will become true and it's calculating in the background. Just note that this uses the vectoral calculation, not true radiance calculation. And if you want to get a more detailed and more accurate sunlight hours analysis, you should use Honeybee, not Ladybug. But this also works as a preliminary understanding. So yeah, it's working, so I'll step ahead and show you what it has done after it has done calculation. So it has completed the calculation. You can see right over here that we have the sunlight hours. It's a bit confusing to understand the legends because the legends of the sunpaths are also showing. So let's hide our sunpath. And if you're wondering how I'm hiding and like unhiding stuff, I'm middle mouse button clicking on top of the component and then disable preview. That way that hides and you can see the hours of sunlight this has gathered over all through summer. And also I should hide the ground plane. So hide that. And now you can see the direct sunlight hours. This also works as your shadow analysis. So if you're wondering how you could create like planting underneath a shaded structure, this would be helpful. And also, yeah, like essentially creating microclimates, full sun plants, partial or shaded plants, things like those, energy efficiency. This kind of analysis like help you to reduce your air cooler load by a lot. So yeah, cooling load a lot. So yeah, that's how you create direct sun hours. So yeah, another layer of analysis. So now let's talk a little about wind diagrams. We're not going to do wind analysis this time. Grasshopper has some beautiful plugins for wind analysis, but instead we are going to create some wind diagrams to understand the intensity of the wind. So the two main wind diagrams that we have at our disposal are wind profile and wind rose. So let's do one by one. Let's get the wind rose first. So the data is going to be the wind speed from our EPW file. And then the wind direction is going to be the wind direction. And here you can see we have a nice all year round wind speed diagram. So what is a wind rose diagram? It is a circular chart, pretty obvious from the view, that illustrates how wind speed and direction are distributed at a particular place over a set of period. So that set of period is going to come from the seasons that we created. You can see here this uses period instead of H or Y's, so keep that in mind. So if you are wondering how this is going to look just in winter instead of all year round, connect period of winter and you'll see that west southwest winds are pretty strong. Also north winds are pretty strong as well. It gives you the meter per second So yeah, that's something. It uses metric system instead of the US feet. So you might need to convert that. Again, summer, if you want to connect that, that also works. Did I connect period? No, I connected HOY. Oh, let's connect period. So period to period, and then you see summer changes drastically. Only the southern wind is very strong instead of the northern wind. There's almost no north wind at all. So again, this is an interactive wind diagram, which is great. So side by side, let's create a wind profile diagram. So that's our wind profile. Met wind velocity is going to be the wind speed. Wind direction is going to be wind direction. And now we have a default 100-meter tall, 100 feet tall. I don't know why this is mile and this is feet. Sorry, this is meter and this is feet. But again, this is feet, so 100 feet tall wind diagram. It's important to understand the wind diagram with direction. So this is north, and this is not true in terms of summer. So we might need to change that. So let's do that. So profile direction. If we hover over that, you'll see 0 is north. By default, we have 0. 1 is northeast, 2 is east, 3 is southwest, and things like that. So we are working with summer. Let's create the 4, and we have a wind that's flowing from south to north. And similarly, if we just change this, we will have a directional change. So that's 3, that's west. So all of those good stuff. So yeah, that's good. We have, and we can also change a lot of different stuff. We can change the terrain height, we can change the profile height and things like those. By default, profile height, as you can see, is 100 feet, but we could change all of those too. So that's all about wind we needed to talk about. Now let's talk a little bit about views. So let me delete the lines first. We don't need any lines for our analysis. Let's talk about viewshed analysis first. So what is a viewshed? A viewshed refers to the geographical area visible from a specific vantage point, encompassing all the surrounding locations in line of sight. So say you are standing somewhere over here and you want to understand your visibility, accessibility, or visibility, not accessibility. You do a viewshed analysis, and in order to do that, you need LB view rows, and you definitely need a point, which is kind of the observer, or you in this case. So that's the point. So let's create a point. I forgot to connect that point, so right click and set one point. Your context is going to be all your surrounding. So let's create a brep. Right click and set multiple breps. And this time I'll also include the ground. Done. And that's going to be the context. And here you can see you have a beautiful view shed. By default, the radius is 500 feet. We could change that. But you can see that the buildings are obstructing the view, and the ground, wherever there's an opening, you can see. So we could also change the view type. By default, it's horizontal radial, but you could do a spherical. So let's do a 2 and connect that to the view type. And that will show you the visibility with a 500 feet radius in a spherical way. So that's one way you could go about this. If you're wondering about your shading structures, this would be the way to go. And then if you do a 3, that's going to be the sky exposure percentage. So let's do a 3. And nothing changed for some reason. So let's do a 3 and do a view type. I wonder what's going on. Yeah, something is wrong, but usually it's supposed to show you the visibility percentage of the sky. So if you're like in a place where there are too many high rises and you're wondering what kind of sky you can see from the ground, that would be the way to go. Right, this morning I have seen sky percentage instead of feet, but now it's showing feet, so that's an error, but I hope it would work out for you. Could be just my PC. So that's how you do a view rows analysis. Now let's do a visibility percentage analysis. So again, that would be under analyze geometry, and this is visibility percent. You can see this is a plural. This says view points instead of point. So if you have multiple vantage points and you want to understand how this is affecting, like your design is affecting the visibility of the overall site, this would be the way to go. So let's create some points. Let's use multiple points command. Let's go to the top and let's create points. I will use the project so that my points are in the ground. So maybe those are the points I need to understand. And then I'll select all the points. It's a good practice to get your points to the proper height of your eye. So let's move all of the points to Z to 5 feet. So now that's a human height. So viewpoints, let's create a point, PT. And while selecting the points inside Rhino, right click and set multiple points. And all the points are now grasshopper points, so connect that to viewpoints. You could create point weights, but I'll keep it as default. The geometry could be something that's in the center, or like in our case, the ground is going to be the geometry because we want to understand how the visibility in the ground is going to be. But if you have a sculpture of sorts, you could use that as a geometry. Let's do a B-rep. Right click, set one B-rep, and set the ground plane. That's the geometry, and let's create another B-rep for the context. Right click, set multiple B-reps, this, and this. Done, and then connect that to the context. You could do like an offset distance, but I won't. And the grid size, let's make it 5 again. That's going to be 5 feet. And then let's see if I'm missing anything. No, we just need to run. Let's save this guy and hit a boolean, connect that, and let's run. So you can see it's pretty obvious. Let's hide some of our stuff so that it's understandable, and let's also hide this. So you can see it's pretty obvious that the buildings are blocking the view. The middle is the most visible, and here's the legend. It's showing the percentage of visibility. Let's see how it changes if we say plant some trees. Let's create some cylinders as tree trunks. Let's copy them. So now that we have some trees, let's unhide everything, hide the ground because that's going to stay the same. But this time, let's right click on the context, set multiple B-reps, and add the trees along with everything else. And you can see the visibility percentage have changed over the plants. So let's hide everything. You can see the trees are having significant impact in terms of visibility. So this is something to think about. Like you might need to create some, you might need to have some trees in your site, but it's important to understand how the trunks of your trees are affecting the visibility of your design. So yeah, compromises. That's what all design is about. You have to compromise different stuff to achieve different stuff. So that's all for today, and I hope to see you soon. If you have any questions, comments, or concerns, ask in the comments. I'll keep all the links in the description section, as well as a more organized Grasshopper file linked with this video. So have a good day.